My name is KIROS BERHANE. I'm a professor and director of graduate programs in biostatistics and epidemiology at the University of Southern California in Los Angeles, USA. This lecture is part one of a short course that was conducted as part of the International Society for Environmental Epidemiology Africa chapter. The course itself was conducted at the University of Ibadan in Nigeria from November 12 and 14. This is going to be part of 2 or 3 series. The first one dealing with the basics of conducting research, focusing on study designs, sample size and power, and also some concepts about epidemiology and biostatistics, such as confounding and others. The course itself will have 3 parts. In the first part, we'll talk about general study design issues. The second will have sample size determination. And in the third part of this, part of the lecture series, we'll deal with related concepts in biostatistics and epidemiology. The slides that I'm going to present today are mostly adapted by a number of short courses and training workshops that were conducted as part of many initiatives, and the slides were actually adapted from contributions from many colleagues and friends. Mainly from workshops that were conducted as part of the Eastern Africa Global Environmental and Occupational Health Hub, GeoHealth Hub for Eastern Africa, of which I am one of the principal investigators. A lot of slides came from the Southern California CTSI, and a short course that was conducted in Ethiopia about 4 or 5 years ago in collaboration with University of California, Berkeley. And also a summer program that we have at USC as part of the SIPS program from NIH called LS Best at USC. And also, lots of slides were borrowed from my colleague and friend John Summit, who is currently at University of Colorado. So starting from study design, the main issues are, in terms of, what concepts we need to pay attention to when you talk about study design. Study design informs how, when, and how frequently measurements will be performed. In designing a study, it's useful to keep in mind throughout the development process of proposals and study plans. And it extends beyond just environmental health into broader issues in any field of endeavor, wherever research is conducted. Of course, we have to realize that no study design is perfect, but giving early attention could lead to better studies. So it's very important that biostatisticians are involved from the very beginning, and it's very important that there is a lot of interaction and understanding and consensus between the subject matter scientists and the biostatistics experts that are part of the team. So what do we mean by study design? Before we go there, then we have to first define what we mean by different aspects or components of what we call population. So, for instance, in this graphics, we have 3 terms, what we call target population, source population, and study population. And each one of these needs to be defined in a very clear and precise way so that what we end up with actually will have some meaning in terms of the hypothesis that we are trying to address. So what we call target population is the group to whom inferences or conclusions are going to be made. And what we call source population is a group from whom the study population is drawn. And then the third one is what we call study population. It's the group that we are actually studying. So there has to be a clear path and understanding of what exactly each one of these 3 types of populations are actually meant to represent, and whether they interact or interrelate to each other in a way that we could make valid scientific inferences from the data. So in defining a study population, it's very important that you have very explicit and predetermined criteria. The criteria needs to be pre-specified, it should be transparent, it should be practical or applicable, and it should have very specific ideas about what kind of participants are going to be included and what kind of participants are going to be excluded. We need to allow for replication so that others could actually replicate the study and do something similar or maybe go beyond it. And it determines the relationship to the source population in a very precise and clear defined way. So when we conduct a study, we want it to be useful. So we have to really point out the issues or concepts that make a study useful. It has to address a relevant and significant research question. It has to have some value. The results in the study population should be generalizable. In other words, it has to have what we call external validity, and I'll come back to this later on. The study population has to be sufficiently large to address the research question. Again, we'll come back to this in the second part of this lecture. The study design has to be appropriate, in line with what the hypothesis we are trying to address. And the study results should not be affected by what we call bias. And this takes us to the concept of what we call internal validity. And I'll come back to this later on to precisely define what we mean by these important concepts. Some basics of study design. First, the first decision is actually to decide whether the study is experimental or observational. What we call experimental is basically where the investigator or the scientist can manipulate the exposure, has some power to manipulate the exposure. What we call observational is situations where the investigator simply studies exposure as they happen in real life. If experimental, then we have to be clear on whether the exposure was assigned at random or in some subjective manner. If observational, then the underlying design has to be clearly defined and properly designed as well. In experimental, we have what we call the randomization to treatment and control in randomized control trial, or there could be other interventions. When we're dealing with observational, we can distinguish between what we call individual level observational studies and population level observational studies. And under that, we actually have different types of designs, which I'll come back to later. In this case, we have defined what we call cohort, case control, or other case-based sampling, or what we call cross-sectional studies, which I'll come back to later as well. So when it comes to types of study design, this graphics actually gives a very clear idea in terms of, kind of the spectrum of the kind of designs that we can consider. It starts from what we call purely descriptive to analytic, kind of going to the gold standard. So we have, disease clusters that can be examined, as they happen or through some things that are happening in hotspots. There is what we call ecological study. And then cross-sectional study comes later on. I'll define all this. And then we have different types of cohort studies, what we call retrospective and prospective. And in between those two, we have what we call case control study. And of course, the kind of gold standard of study designs is what we call experimental studies, where the investigator has maybe not full, but some control or some well-defined control in terms of who is getting what kind of exposure. So we'll come back to some aspects of this a little bit later in our lecture. So in randomized study, basically we start with a population. And what happens is basically then we have random allocation where some people are exposed and other people are not exposed. And then once the exposure status is determined by the investigator, then we try to see how many people develop the disease under study or the condition under study and how many do not. And we try to see whether there is a difference in this kind of allocation or happening of the disease or condition under study in the exposed and unexposed population. And when we are dealing with observational or non-experimental, could be randomized study, then here it could be self-selection. In terms of, one example is self-selection, of course, but there is non-random allocation here. We start with the population, then some people are exposed and others are not, and we don't have any control over this. And then we also try to see how many of those exposed develop the disease under consideration and how many do not in those two groups that happen as things develop naturally. So the question is, obviously, I think in order to randomize, in order to have full control, it comes at a price. So why randomize? What's the value of randomization? Randomization actually helps, in the sense that the group assignment does not depend on participant characteristics. So it actually assures comparability on potential confounding and modifying factors. And I'll come back to some of these concepts which are not well defined yet. It also assures comparability on any unknown factors. So if it's truly random, then I think you're trying of controlling some unknown factors as well. But there is also a misconception in the field. Some people actually think that if you have some systematic or haphazard assessment, they try to, or they kind of mistakenly identify that as randomization. But there is a very precise and clear definition of randomization, which is not synonymous with systematic and haphazard assessment that could actually look like randomization, but it's not in real life. Now, before I go further, I would like to define some concepts because they will come back, they will come up several times before we go to these fundamental concepts in biostatistics and epidemiology towards the end of the lecture. The first one is what we call causal relationship, or what we call association when you're dealing with observational studies. You have some cause or some factor on the left-hand side of the of this graphics, and we have an effect that follows from the cause. So this is kind of a causal relationship in statistics or in epidemiology. Usually we deal with associations because we don't have a causal effect that we can actually go after. The second concept, important concept, is what we call confounding. And here what we have is, even though we have a factor and the factor is somehow leading to an effect, there could be another characteristics that's actually related to both the effect and the factor. So if we do not account for this, what we call confounder, then I think you might attribute things that are not supposed to be attributed to the factor. So this is something that we need to adjust for in the analysis stage, and we call it confounding. The other important concept is what we call effect modification, or sometimes people call it synergy or interaction. And here basically the relationship between a factor and an effect is essentially modified by some factor. For instance, if you're talking about the effect of air pollution on asthma development, then whether the participant is male or female could make a difference. And therefore, that could actually be an issue that we need to account for in the analysis stage. Some issues to consider. We need to be clear about the research question of interest. We need to be clear about the intervention to consider. We need to be clear about what exactly is being compared. We need to be clear at the outset what the length of the study is going to be, what type of data you will be collecting and how often. And of course, the reality check is what's your budget and how do you optimize resources. And here is actually where the issue of trying to come up with the right sample size that will allow you to make inferences in a valid way, but at the same time try to optimize resources as well so that you can get away with minimum possible, but to be able to address the question of interest. So let's give an example. So a question that we can consider could be, for instance, does use of a clean stove reduce the risk of chronic obstructive pulmonary disease in women, or does it affect the risk of mortality in under 5 children? So this is a very well laid out and clear hypothesis that we can go after. And then based on this question, we can go ahead and try to come up with study designs and research questions and so on and so forth. One kind of study that we can conduct is what we call cross-sectional study. And here basically what you have is you have two groups. One group is assigned to traditional stoves. The other group is assigned to LPG, which is a clean stove group. And then measurements are made at the same time. So you have the stove usage, and you also look at the outcome at the same time. So it may show an association, but it's very difficult, as you can imagine, to establish causality because both the exposure and the outcome are happening at the same time. So there are some practical advantage, but there are also issues that we need to be aware of. For instance, in cross-sectional, of course, you identify groups and take measurements. It can occur quickly and relatively inexpensively, and therefore that's actually the practical value. You can study several outcomes. It's very good for hypothesis generation. It yields, for instance, prevalence estimates, but it does not establish sequence of events. And therefore, this could actually have serious issues with bias. And therefore, this is actually exactly the reason why on that spectrum of studies, it was actually on the left-hand side, on the low end, because of this lack of temporality or sequence in terms of how the exposure is following the outcome. Another study design is what we call case control study. And here basically what we're doing is simply comparing individuals with a specific disease, which we call case, to those without the disease, which we call controls. And therefore we're starting actually with the outcome. So we have a number of cases and then either 1 to 1 or 1 to 2 or 1 to 3 controls for each of the cases. So we're starting with the outcome. And therefore we're trying to see what this case and the controls were exposed to. And as you can imagine, this is actually very useful when you're dealing with rare conditions. Because if you start with a population and you're following people over time, if it's a very rare condition, 1 out of million or 1 out of 100,000 getting it, then you will have to wait for a very, very long time to get enough cases. But if you start with a case control study, then you can actually start with a number of cases that you want and matching controls, and therefore you go back and study the exposure. And this is actually a perfect graphics in terms of, among all the animals, you only see one zebra, but the majority of the animals are actually, non-zebra animals. Therefore, in that case, then I think this is an example of a rare condition. So in this case, you have unexposed and exposed, and then people without disease, which are controls, and then you have exposed and unexposed people with disease. These are the case, but the investigation or the study actually starts, as you can see here. Basically, you're starting from the outcome side, and then you're moving forward. Even though time always marches forward from the left-hand side to the right-hand side, but the investigation is actually backwards. And therefore you're kind of establishing the fact in terms of what happened based on whether someone was a case or a control. One issue here is how to select controls. It's useful to think of the study base. That's the underlying population that gave rise to the case. And here the assumption is that individuals in the study base are representative of the same basic experiences. And controls should be at risk of developing the disease and represent the same underlying population, which also gave rise to the case. So most of the time, actually, people match on age, sex, ethnicity, and other demographic or socioeconomic status variables, so that we don't have to worry about them. If we have done our job right, we don't have to worry about them when it comes to the analysis stage. Okay? All right, so this is one example which I'm not going to go to, but you will have the slides, and then you can look at the COPD example simply as a concrete, case that you can investigate. So, as I said, case control studies are useful for rare disease. You can study multiple exposures at a time. Remember, for cross-sectional, we said multiple outcomes. It's relatively inexpensive, and you can do it in a very short duration. It's very difficult to reconstruct historical exposures sometimes, and this could be a problem. And sometimes selecting controls could be very challenging. So even though it has a lot of values and a lot of practical implications, but there could be some challenge as well that might actually lead to some sort of bias. The other kind of studies are what we call cohort studies. And basically here we're defining a group of people, and you simply follow them through time in order to observe, how many of them get exposed to one or another kind of exposure, and between those multiple groups, how many of them develop the condition under study, and how many of them do not develop the condition under study. So here you can distinguish between what we call prospective and retrospective. In this case, what we are doing here is this is actually a prospective cohort study. You start with the population, and the investigation is starting here where the lens is, and then you start with people without disease because you're trying to see, who is exposed and who is not exposed within the study period. So you have to have a clean population to start with. And then out of those exposed, how many of them develop disease or condition, how many do not, and the unexposed one also. And then you try to compare, whether being exposed actually leads to more of the condition or less of the condition. So the time and the direction of inquiry are actually going in the same direction in this case. Okay, so here you're identifying cohorts, follow through time, collect data on exposures and disease. It's a gold standard of observational studies. Of course, it's expensive, especially if you're dealing with a non-highly prevalent condition. Logistically expensive and intensive. It could cost a lot of money, and you have to wait for a long period. And it's very difficult to conduct such kind of studies for rare disease for obvious reasons that we have discussed already when we talked about case control studies. The other kind of study is what we call retrospective cohort study. Again, time is always marching forward, but as you can see here, even though it's the same graphics, the investigation is actually starting from the disease stage, and then you're reconstructing the exposure history. You're basically reconstructing the cohort study by moving time backwards and then try to, to see what happened in real life, even though you're starting from the end. Okay? All right, and then here, of course, it could be quick, cheap. You can have multi-cause study, and this kind of studies are common in occupational epidemiology. And sometimes the problem here is, of course, it's difficult to reconstruct historical exposures. So this could lead to, some issues of bias. And of course, as we said earlier, experimental studies are kind of the gold standard. Here you have control over the intervention, and also, you have, full knowledge about, or full control about who is exposed and who is not. It controls for influence of confounding variables. You can manipulate the exposure, and you have key features. Other key features are control group and randomization. And this is kind of considered as a golden standard of study designs compared to the others that we have talked about. Okay? Again, it could be costly in time and money. It produces the strongest evidence for cause and effect. Of course, you have to be very narrow and explicit in your research questions. And sometimes when you try to customize interventions, this could limit generalizability. There could be some ethical issues that you really have to pay attention to. And the potential for what we call observation and inclusion in a study, inducing change in behavior is possible. This is sometimes known as the Hawthorne effect. We're not going to go into that in any detail. There is also what we call placebo effect that you also have to pay attention to. Usually we have double blinding in order to make sure that we don't have the placebo effect in conducting this kind of designs. So this is actually the end of the first part of this part one of the of the series, and the next one we're going to talk about is how to determine how many participants to include in a study. This is what we call statistical power and sample size considerations. And again, the material for this part is also adapted from the different sources that I have indicated or acknowledged at the beginning of this lecture. So some important concepts to pay attention to. When you talk about power, statistical power is really what we call the likelihood that a study will detect an effect when there is an effect to be detected. It's a little bit of a mouthful, but hopefully it will be clearer as we move forward. So in our examples, this could be the chance of detecting a difference in a household air pollution due to an intervention when there really was a difference. So that's actually what we call statistical power. And we'll try to be a little bit more explicit and exact about this definition. There is also this big concept of p-values, which is also another complicated concept. It's basically fundamentally the percentage error rate of stating that there is an effect when there is in fact no effect. So this is kind of an error, and this is actually where you control what we call type 1 error, which I'll come back to later. It gives you like kind of a cutoff in terms of what kind of p-values would actually lead to significant effects versus non-significant effects. And of course, most of you know the magical 0.05 cutoff value for this, which basically indicates that there is a 5% chance or probability of thinking the intervention reduces household air pollution, versus not, and when there is no effect. There is also this big concept of detectable difference. What kind of magnitude of difference we are actually interested in, and this could have a big impact in terms of how many participants we will need in order to reach valid conclusions. Most of the time, 80% power to detect a difference when there is one, or to detect an effect when there is one, and a 5% chance of committing this error of saying there is an effect when there is none are kind of commonly used in practice. I'm sure most of you listening to this lecture also have used this kind of magical cutoffs. Okay, so why do we care about sample size determination? Well, suppose you want to design a new study. Then how can you determine what the sample size is going to be? So it's very, very important for the success or failure of a study to find interesting results. You want a study that's large enough to have an adequate power for detecting association of interest, but you don't want it to be too large so that it's going to be unnecessarily expensive or time consuming. If the sample size has already been determined due to some issues outside of your control, for instance, if you're studying childhood asthma, but there is a fixed number of cases that he can possibly get, then that could be your starting point. Then it becomes important to understand how much power you can have to detect an association for the given sample size of interest. And of course, if you have submitted any grant proposal to funding agencies like the National Institute for Health or other funding agencies, then any grant proposal requires a very well laid out and very thoughtful section on statistical power and sample size considerations in order to be funded successfully. So it's a very important concept to pay attention to. So examples of N are dictated by the available resources, of course. And in fact, when we were giving this course, there were 72 participants, and that could be basically, something that you can start with and then conduct a study on, or sometimes you have more control about what the sample size is going to be. Like for instance, when you're conducting an intervention study, then depending on how much resources you have and how much time you have, how much money you have. Then I think you can have some control over the sample size, but not much, of course. So let's go back to this issue about what is statistical power. Statistical power, as I said earlier, is the probability or the likelihood that you will reject the null hypothesis, where we usually say there is no change or there is no effect, when the alternative hypothesis is true. So there is a true effect of X on Y, and based on your sample and statistical analysis, you actually reject the null hypothesis. All right, so when you try to conduct a test, this is the way it goes. Basically, you have a null hypothesis, and the truth is basically that null hypothesis either could be true or false. There is no other possibility, right? But when you collect your data, you conduct your study, and you reach a decision, then you also have two types of decisions. You either accept the null hypothesis or you reject the null hypothesis. So you basically have essentially a 2-by-2 table where the truth is, which most of the time is unknown to you, and what you can decide based on the sample size that you have under consideration. So if you accept the null and it's true, then you have actually made the right decision, so there is no error. If you reject the null and it's false, you're also in the right, so there is no error. The problem comes when you actually reject the null hypothesis when it's true. So that's what we call type 1 error. And this is actually the one that leads to that 5% level of significance. And if you accept the null hypothesis when it's false, then this is what we call the type 2 error. And the complement of this is actually what we call statistical power. So essentially, this is what I just said in the previous slide. In the blue, you have alpha, which is the probability of a type 1 error, which is simply what we call significance level. Beta is usually by convention the probability of a type 2 error, which is kind of in this kind of lighter blue color. And then you have the power, which is simply 1 minus beta, which is probability of correctly rejecting the null when the alternative is actually true. So essentially rejecting the null when it's false, which is exactly the right thing to do. And this is what we call statistical power in our sample size calculations and in biostatistics. So what role does N, or the sample size, play? For a given study design, significance level and hypothesized level of association, then a study that has larger sample size will lead to more statistical power than a study that has smaller sample size, which is intuitive. So the general guideline in study design is basically try to obtain the largest sample size that the budget will allow, provided quality of data is obtained or maintained, homogeneity of study objectives is also maintained, and therefore you have a valid study. Now the question comes, how do we calculate sample size? For many types of hypotheses, there are well-developed formulas that we're not going to go into a lot of detail on, but we'll give some examples that can be used to estimate sample size and also calculate statistical power. So if you want to perform a study in which the number of subjects are randomly assigned to a drug group or a placebo group to determine whether the drug reduces, let's say, a condition like cholesterol, as an example, then based on the kind of preliminary data that you have on what the parameters of this kind of situations is, then you can go ahead and do your sample size calculations. So there are some assumptions that you have to make, as in anything that we do in statistics or biostatistics. Let's say, for instance, let's assume the outcome is continuous, and we most of the time assume that it's normally distributed, even though sometimes it could be skewed. Let's say the null hypothesis is that there is no difference between the mean outcome in the drug group and the placebo group. The placebo means simply something that looks like the drug, but it doesn't have the chemical components that makes it, the drug as under consideration. Let's say you're trying to conduct a two-sample t-test that can be used to test the hypothesis. Random and equal allocation of subjects to each treatment group will give you basically n/2 on the drug side and n/2 on the placebo side. And then you have to decide, what kind of difference you're expecting. So in this case, we are expecting the drug to reduce cholesterol by 10 microgram per deciliter, and therefore, that's basically the detectable difference that we are going after. And we also have to have some idea about the variability. Here we have sigma equal to 30, perhaps estimated based on prior study or some pilot study that you have to conduct as preparation for this actual study. And you have to determine what the level of significance, the amount of error that you're willing to tolerate in order to reject the null hypothesis when it's true. And we also have to decide whether you're talking about a two-sided test, whether you're simply trying to test whether there is any difference or whether there is any directionality, whether you want the mean of the drug to be greater than the placebo or vice versa as your alternative hypothesis. And finally, you have to decide what kind of power you're going after. And most of the time, as we said, 80% is kind of the standard practice in terms of going after statistical power. So for a two-sample test of means, again, without going into a lot of detail about where this came from, you basically have to have all those elements, like the detectable difference, which is the delta in the denominator, the variability in the outcome, which is sigma square on the numerator of this equation, and then you need to have kind of the the division in terms of what proportion you want on the drug side versus the placebo side, and of course, the normal distribution quantiles that will give you the level of significance at 5%, let's say, and the statistical power at 80%, in this case, 0.2 being the type 2 error probability. So all these factors actually come into play when you try to calculate the sample size of any given study. And if you're assuming that there will be enough equal allocation for the two groups, then the formula actually becomes even simpler, and then you can go after the calculation of the sample size. So the Z alpha, which is associated with a 5% level of significance, will give you a quantity on the normal distribution of 1.96. I'm sure most of you know this value. And then what we call Z beta, which is associated with the power, also will have on the standard normal distribution, which means your invariance 1, a value of 0.842. And then, of course, the detectable difference is 10, and the variability or the standard deviation is 30, so for the variance is actually 30 squared. So if you plug in all these values into your formula, then you end up with 283 subjects, or participants to be part of this study in order to have 80% power to detect at least a 10% difference in the two mean values for the two groups. Okay? So essentially you will have roughly about 142 per treatment group as part of this study. And of course, most of the time, we don't do this by hand. So there are, we can either write our own code, or we can actually use some off-the-shelf software in order to calculate sample sizes. So here actually is an example of what we call the R software code, we can simply translate the formula that we had in the previous slides into R. Since we have not talked about the R course, even though in the actual course we spent quite a bit of time to go through the basics of the R software, but in this case, because we have not done that, I'll simply make this code available to you, and maybe when we come to the second part of the lecture series, then we'll have a chance to go back to the basics of R so that you can actually go through the steps that are outlined here. But it suffices to say that actually you can translate the formula into our function, and therefore you can automate this process so that anyone could actually use this formula in order to come up with a sample size for varying values of the detectable difference or variance estimates or power value or level of significance of interest. All right, again, this is a little bit more of detail, which I'm not going to go into. The other flip side is, of course, you can either calculate the sample size or you can calculate the power given the sample size, and you simply have to rearrange the formula in order to basically either focus on power calculation or focus on sample size calculation. And in this case, it's showing that if you indeed use 283 as your sample size, you'll actually have a power of 80% coming back to you. So this is kind of proof of concept in terms of exactly getting what you started up into getting. The other thing you can do is actually you can vary the values, either the variance or the power or the detectable difference, and you can calculate these numbers for a range of values, and you can graph so that the investigator can have a sense or an idea of where to spend resources and how much to give up or how much to gain by including more participants or excluding participants from the study. This is one example that you can actually do. In the previous page, actually, there is a loop that has been already built into the function that we have created in R. And therefore, you can ask for the software to plot it for you, and you can get a range of what sample size would be required or needed in order to achieve what power. And as you can see, if you're really willing to go with small power or with low power, then you can get away with smaller number of participants. But if you're going for higher power, then the price is, of course, that you have to collect data from more participants. And of course, everything that I have said here, now that you have the code in the previous slides, you can actually try it yourself, either write the code yourself, understand it, and try to vary values so that you can actually come up with your own understanding. Of course, you don't have to do this, even though we try to actually do it in real time so that you understand the concept. The R software itself actually has the code built in, so you can use what we call power t-test in order to make calculations for the t-test without having to do your own calculation as well. The other software other than R, which is quite popular these days, that I would like to introduce is a software that has been developed at the University of Southern California over a number of years ago called Quanto. This is freely available software, and you can easily download it from the ISEE website, as you can see from this slide. Currently, it deals with Windows-only platform, but more general version is in development. It was primarily designed for genetic studies or gene environment interaction studies, but we have been using it for many years for any types of designs as well. It covers several study designs, different types of outcomes, and I would like to actually give credit to my colleague Jim Garderman and John Morrison at ISEE that have developed this program over several years. And as you can see, it has been downloaded and used by investigators from all over the world, currently more than 100 countries. So the hope is, of course, after this lecture, researchers in Africa will also be using this software because it's freely available and also it's very, very user-friendly. And I'm not going to go through the details, but essentially it's a window-based program. It allows you to make a choice about the hypothesis, what you're interested in this case, gene-environment interaction is of interest. You can actually try to decide on what kind of outcome or design you're going after, and you can choose what the prevalence is, if it's binary outcome, or what the standard deviations is if it's the a continuous outcome. and then you can try to determine what kind of main effects you're trying to detect, and then you try to select either you're going after power or after sample size, and there are buttons that you can choose one way or the other. And of course, once you have made your choices, in this case, actually, we try to replicate exactly the studies that we actually try to implement using the R software. And here also, it gives you an N of 283. In fact, in this case, it gave you 279, but this could be due to the type of tests that actually are underlying the development of this software. But essentially, you end up with a ballpark similar numbers. So this is kind of a proof of principle. All right, so far, we have covered 2 parts of this lecture, and the third part is the fundamental concepts in biostatistics and epidemiology, such as confounding and others. And again, the same source of materials was used in order to be able to put the material together for this. This is the same slide I showed you earlier, causality or association, the concept of confounding, and the concept of modification or effect modification sometimes. Sometimes people call it synergy, sometimes people call it interaction, but it's essentially the same concept. So we're not going to go over this again because we already talked about it, but we'll go into a little bit more detail about each one of these concepts. So causation, okay? You can have smoking leading to lung cancer, or smoking leading to some carcinogens and then lung cancer. And then you could have the relationship between smoking and lung cancer, which pass through the carcinogens being modified by genes. And then you can have something a little bit more complicated as well, where you have the tobacco companies smoking carcinogens, lung cancer, and then of course different people with different genetic makeups are actually having different reactions to the smoking lung cancer association. In terms of confounding, basically, as I said earlier, a confounder is associated with both the factor under study and the effect. So it kind of confounds the effect of the factor under study. So even in its lay English term, actually, you're basically trying to confuse you in terms of what the relationship between the factor and effect is. Either it is attributing something that belongs to another factor, or it's kind of giving away some. Therefore, I think you have to pay attention to these kind of confounders in order to have a clear relationship between the factor under study and the effect under study. And you can imagine your own examples in your own studies actually in terms of how this would be defined. A modifier is basically something that, a situation that happens when the magnitude of a factor's effect on the outcome actually depends on the presence or level of another factor, that other factor is modifying how the factor and the effect are actually related to each other. So, finally, when is a study useful? Well, a study is useful, of course, when you're studying a significant research question. But it also have to have internal validity. In other words, results should not be affected or should not be unduly affected by error. There will always be an error, but we have to minimize and, to the extent possible, completely eliminate it. And here actually you have issues like confounding, what we call systematic error or bias, and this could be what we call selection bias or information bias, and I'll come back to this later. There is also the issue of random error. So in other words, when you have an underpowered study due to insufficient number of participants in order to address a research question. And of course, variables have to be measured without error, but in most of the time actually, there is no good precision in the variables being measured. So there is error introduced into the measurement that we get as well. There is also this issue of external validity. So the results that we get should be generalizable to a definable population of interest. If you're trying to make a decision about asthma development and how air pollution affects asthma in the US population, then the study population that you have under consideration should be representative of the target population that you're going after. Remember, I'm actually taking you back to where we started at the beginning of this lecture in terms of the target, the source, and then the study population. So for instance, let's say the target is all asthmatics, and the accessible population is asthmatics in some village in Africa. I'm going to call it Village Africana. And then you have the intended, which is asthmatics that are accessible to the researcher and also meet some inclusion criteria. So these criteria also could redefine your population unless you're very careful. And then finally, in your study, you have the asthmatics in the trial itself, right? So you have all these, arrows that are going after, and any mistake or misstep in these arrows could actually completely invalidate in terms of how accurately you can go back to what you intended to study in the first place. So the issue of internal validity basically is, in that, difference between the intended and the study. And then you have the generalizability also is again what we have in the trial in terms of the number of asthmatics or the type of asthmatics, and then how they relate to the all asthmatics as in the target population as well. So this is something that you really need to pay attention to, because even a well-intended study and well-run study, if it has missteps in some of these key steps, then I think it could lead to something that we did not intend to study in the first place. So selection bias. So what do we mean by this? In this case, you're basically asking the question, are the results affected by who and why participants got into the study or remained in the study? Okay, so that's one thing that you need to pay attention to. That's the question you're really asking when you talk about selection bias. Information bias is essentially in the case where you're asking the question, are the measurement tools and processes used to assess variables accurate and they measure the truth? So that's the other question that's fundamentally important. So how do we define a selection bias? Selection bias is really distortion of the true effect size in the source population, or what we call the intended population, when calculated in the analytic population. So the distortion could actually result from, let's say, procedures that are used to select study participants, or some factors or procedures that influence study participation, factors that could determine or influence lost follow-up, or factors that might influence missingness in the data. And the impact of all this, or any of this, or a combination of this, could be that the effect size measured in the analytic population is going to be different, either over or underestimated from the source population. In other words, those eligible for the study, including those who did not participate. Okay? So again, we're coming back to this issue of source, to the study population. This is the same cartoon that I showed you earlier, but now you have the analytic population at the top, and then you're basically trying to go from the source population to the analytic population. So what happens? So essentially, when you go to the actual conduct of the study, you have the ineligible part, and then from those eligible, those who do not participate and those who participate. So the true effect size in the source population is going to be representative of the eligible individuals who do and do not participate in the study. Okay? So example 1, okay, you have the studied effect size, which is the odds ratio, which a concept I haven't defined, probably will come in the second part of this lecture series, is 1.4. Procedures used to select study participants and factors that influence study participation basically led to 1.4. However, the true effect size actually is 2.4, right? Which is on the left-hand side. So what was the impact of selection bias, right? In this case, it's underestimation of the true effect, okay? But that's not always the case. Sometimes it could also lead to overestimation of the true effect. So essentially, you have the true, which is 2.4, but you're actually underestimating into 1.4. Depending on whether this is significant or not, it could actually have a serious impact on what you conclude from this study, and it could either, completely distort practice and could have huge implications in terms of public health, but also monetary issues if you're developing a new drug. Okay? So the result is negatively biased in this case towards the null due to selection bias, and therefore that study has underestimated the effect. Okay? And then if it's on the negative side, then of course I think it's going to be overestimation, which I think this should be immediately intuitive to whoever is listening to this lecture. There are many factors that influence participation. It could be the educational level of the participants, or it could be the state of the health of the participant, severity of the condition, or some other factors. Risk factor distribution, it could be race, ethnicity, it could be presence of disease, many factors actually come into play. So, there are many situations where selection bias is actually more likely, and there are some examples here basically that would lead to that kind of situation. So, in terms of selection bias, let's say if you have an eligible source population and you have outcome yes or no, that's on the top side, essentially here, and then the exposure is also yes or no. So you have some people that have yes for the outcome and yes for the exposure, A, and then no yes is B, and then outcome yes, exposure no is C, and so on. And the odds ratio is basically defined as a ratio of the A times D over B times C. Again, it's something that I haven't explained. Again, it will come later on when we talk about the biostatistical concepts. But for now, let's say this is a formula that will give us the odds ratio between these two conditions. And therefore, actually, this kind of numbers, when they are more than one, they basically show that there is more risk, as for the outcome as when you are exposed. But when the odds ratio is less than one, essentially we say there is protective effect of the exposure on the outcome, just for now. But later on we'll come to it in a much more structured way. Okay? But let's say in the study population, what you end up with is something like this. So you start with basically A is not only A1, but it's a combination of what we call A sub 1 and A sub 2. And then you have B is, two components, B1 and B2. C is the same thing, and D is the same thing. So even though this is what you're going after, essentially this is what you're going to observe from, the study population that you have under your control. So the real question is the ratio AD over BC equal to A sub 1, D sub 1 over B1, C1? If the answer is no, then basically you have some sort of selection bias, which is systematic enough to distort the findings of your study. So essentially what you have is, you have the source population disease situation, and you have the study population disease situation. And the issue is whether these things are lining up, right? Okay? And I'll give a specific example, essentially, from the previous example, how this actually will play out. So if things cancel out, then you're going to be okay. So for instance, if the relationship between A sub 1 and uppercase A is simply F1 times A, and then each one of the others also have F2, F3, and F4, then the relationship between the odds ratio for the study population and the relationship between and the odds ratio for the target population are essentially going to be like this. So if F1, F4 over F2, F3 is essentially 1, then you're okay. But if that ratio is going to be either smaller than 1 or bigger than 1, then you have an effect of selection bias. That's essentially what's going on. There are many examples of selection bias. Again, we're not going to go into all of these today. But I'm simply listing them. One is one that we have already talked about, self-selection. Then you have things like Bergsonian, selection bias, selective survival and lost follow-up, or healthy worker effect. These are, terms that you might hear about. So I'm just listing them here, but we don't have the time to go through each one of these in the time that we have. So, for instance, in self-selection, you have what we call voluntary and non-response bias. This actually goes through an example between chronic obstructive pulmonary disease and smoking, and how things actually relate to each other in the target population and in the study population. You essentially start with 60, 30, 40, 50, as you have here in the top, 2 by 2. And what you're studying is, or observing, is basically in the bottom. Then if you keep forward and try to see the relationship, then things are not lining up properly. So going from 60 to 40, you have a 66% reduction, whereas going from 40 to 35, you actually have about 13% reduction. Ending up with 87 of the of the 40 actually happening in the disease. So The true odds ratio that you're trying to go after is 2.5, but you don't know that. But the odds ratio that you're ending up with is actually saying 1.9. So this is an underestimation of the odds ratio simply because of this selection bias. So the issue is, how do you deal with selection bias? It's important enough that actually could lead you to wrong conclusions. Of course, you have to worry about it. And in order to avoid it, there are certain things that you can do, like, you have to try to optimize the response rate. And you also can try to measure it, try to define the source population, try and obtain information on non-participants, lost follow-up, and try to prevent, missing data. Or at the very least, actually, you should conduct a very thorough sensitivity analysis after your main analysis in order to see whether there is any source of bias in your findings that you should be aware of. Another issue is information bias. Again, here what you have is this issue about how does the quality of variable measurement impact internal validity. So you have truths in the universe, truths in the study, and then findings in the study. So you have the research question, the study plan, the actual study, and then you have the target population, accessible population, and study population. And then finally, you have this phenomenon of interest, intended variables, and then the actual measurement. So each one of these actually has, this issue of external validity and internal validity. This is actually modified from Hawley's designing clinical research material in order to actually line up with what we are trying to study today. So the process of measurement, you have to identify and describe health-related phenomena, variables that represent the phenomenon of interest, and then you have to choose a measurement scale for each variable. And of course, there are many ways that you can actually, choose measurement scales. And each one of those have their own characteristics, and you have to really pay attention to. Again, I'm not going to go through this table in the interest of time, but it will be available to you to study it, and I think it's kind of self-explanatory in a way. So please try to take the time to, study the contents. And of course, the issue of accuracy and precision is another concept that actually you need to really have a clarity on. What we call precision or imprecision is basically lack or presence of random error, and accuracy and inaccuracy is basically whether you're trying to measure the truth or not. Okay, and then there are certain definitions, best ways of assessment, what the value to the study is of precision and accuracy, and what really cause, what the consequences or what the causes are of lack of precision or lack of accuracy. So without going to the details from that, then let's try to use this cartoon as well, which is adapted from Hawley designing clinical research 4th edition as well. So we have different situations here. Essentially, you have these 4 things, and I have deliberately blocked the rectangles in the bottom. But if you go one by one, you can actually try to see what the situation is. So in the first part, you have good precision but pure accuracy. You're not accurate in getting the bullseye. In the second one, you have poor precision, so you're all over the place, but probably have good accuracy because on average, you're actually kind of ending up in the middle, which is kind of in a very strange way. You still have accuracy even though your precision is actually really wanting. And then the third one essentially has the best. Basically, you have good precision and good accuracy. You're basically hitting the right target. And then poor precision and pure accuracy is basically you're all over the place, but you're actually only on the one side of the circle, and therefore, even on average, you're not going to be right. So I think these are kind of very clear indications of what the difference between precision and accuracy is. Again, here, what do we do about information bias? Of course, we have to worry about it. So essentially, people do quality assurance for all data items. They try to carry out validation studies. They try to do bias analysis, for instance, by conducting thorough sensitivity analysis on the real data, or conducting simulation studies where you actually know the truth or the answer, and therefore you try to see whether your procedures lead you to those kind of conclusions. And you have to the extent possible, make adjustment for error in the analysis as well. So coming back to the what makes a study useful, you have significance of the research question is very important. Internal validity and external validity are also very important. And we went through a number of concepts that are actually very important and try to have validity both internally and externally. And of course, to begin with, you have to have a question that's worth studying. So this will be the end of part 1 of this series. When we come back to the second part, we are going to concentrate on fundamental concepts in biostatistics, in actually, kind of focusing on the how of how to conduct, a study and how to analyze the data that we collect, and how do we try to minimize, issues that are, related to how to tease out the right conclusion from the samples that you have collected. So with this, we'll end up for today, and we are going to stop here. In part 2, we are going to come back with fundamental concepts of data analysis and biostatistics. Thank you for listening.